What's up guys, it's James here, and for today's video, we will be discussing the finite difference formula using Taylor series. But before we dig deep to our topic, let us first recall the key concepts that will be used in this lesson. So let us recall differentiation. We all know that differentiation is used in measuring the rate at which a quantity changes. For example, in the velocities, slope, maxima, and minima of functions. But differentiation can also be used in approximating values. So how does differentiation can be used in approximating values? Okay, so let's take a look at this graph right here. Okay, so the graph contains a set of points and the interval between points must be equal to each other. We will call this point as point A. Okay, so the points after the point A are what we call the neighboring points. Okay, let's put the name of the variable. We can call this one x1, x2, x3. These are the neighboring points. Okay. So the neighboring points are used to approximate the value of a certain function. So let's start first by creating a tangent line from the base point A to each of the neighboring points. Okay, let's start with this one. For the first one, for the second one, and for the third one, okay, right here. Okay, let's redraw the line, the points. Okay, there you go. And along point A, there is a tangent line. And this tangent line right here represents the true derivative of the function A. While this 3 represents, okay, this 3 tangents right here represents the approximate derivatives. You can notice that as the neighboring points gets closer to point A, okay, this one, as this points gets closer to the base point A, the value of the approximate derivatives gets closer to the true derivative. This means that the closer the points are to each other, the accuracy of the approximated values increases. Okay, so this concept can be described in this equation. F prime of A is equal to the limit of f of x minus f of A over x minus a as x approaches to a. This concept is used in finite difference formula in which the derivative is obtained by taking a point x near point A and calculate the slope of the line that connects the two points. Now in this lesson, we will be deriving some finite difference formula using Taylor series. But before that, let us discuss first what is Taylor series. Okay, and some books call it as Taylor series expansion. So what is Taylor series expansion? So Taylor series are in estimate used in estimating values of a function on an interval. And this interval must be equal to each other. Okay. So the Taylor series is described in this equation. F of x is equal to f of a plus f double prime a over 2 factorial times x minus a squared plus f3a over 3 factorial times x minus a cubed, so on and so forth. So in Taylor series expansion, the more terms you will be adding to your equation, the accuracy also gets higher. There are different ways to formulate the finite difference formula, and the accuracy of the values obtained depends on the order of the derivative and the number of points that is being considered. Okay? Okay, for the first order derivative, okay, first derivative, we can use the following formula. Okay, let's start first with the 2-point forward difference. So 2-point forward difference can be illustrated in this graph right here. Okay, the same with the graph earlier. A set of points are being plotted along this one, and this set of points represents a function. Okay, again, the distances between these points are constant or the same. So we will call this one as the base point x sub 1, and the next neighboring point is the x sub 1 plus I plus 2 right here. So in 2-point forward difference, we will be considering the nearest neighboring point to the right of the base point. So the base point right here is the point x sub I, and the nearest neighboring point to the right is the x sub 1 plus I. Now we will draw a tangent line that connects these 2 points. Okay, that one. And again, we will show the true derivative that is being represented in the tangent line. So this one right here is the true derivative, while this one right here is the approximate derivative. Now, using the Taylor series expansion with the remainder, okay, let's put the equation right here. F of x is equal to f of a plus f1 of a times x minus a plus f1 of prime. Okay, now, since we have different names for our points right here, let us convert the given. Okay, for the value of x, we have, okay, for the value of a first, a, we have the x sub I. Now for x, we have x sub I plus 1. Now for x minus a, we can call it as h. Okay, so now with all this given right here, we can rewrite the function or the equation of the Taylor series as f of xi plus 1 is equal to f of xi. So since we are looking for the derivative, for the first derivative, we will be isolating f prime of x to the left. F prime of x sub I is equal to f plus 1 minus f x sub I over h plus k. So the last term in the equation is what we call the truncation error. Okay, this term right here. The second term of the equation introduces the truncation error. Since this term is proportional to h, rewrite this as this one. We can rewrite this as OH or order of h. And this symbol right here represents any value between x sub I and x sub I plus 1. Now for the second one, the second formula, the 2-point backward difference. Okay, to better explain this one, let's create a graph right here. Okay, so we have set of points here, and this point right here is the base point xi. So in 2-point backward difference, we will be considering the nearest neighboring point to the left of the base point. So the nearest neighboring point is this one. We will name it x sub I minus 1. So so we will be drawing a tangent line that represents the approximate derivative of the point x sub I minus 1. Now again, we will draw the true derivative right here. Okay, let's write here true derivative. Well, this one is the approximate derivative. Okay, so the solution in deriving the formula for the 2-point backward difference is just similar to the 2-point forward difference. The only thing that is different is the variables being used, because here in 2-point backward difference, we use the point x sub I minus 1 as the nearest point. Okay, so let's put the given right here. So for A, we have x sub I. For the x, we have x sub I minus 1. And the value for x minus a is just the same, the variable h. So now again, using the formula for the Taylor series expansion, okay, you have f of x is equal to f of a plus f prime of a times x minus a. Okay, now substituting the variables that we get for this problem, we have for x, we have x of I minus 1 is equal to this one times h plus h squared. Okay, so isolating the value for f prime of x I, we have it here. So, okay, so the second term OH is just the same to the variable that we have in the forward difference. Okay, this represents the truncation error. The formula for the forward difference is this one. I mean backward. Now for the third formula that we will be deriving is for the 2-point central difference. Okay, let's consider a graph right here. And a set of points right here. So the point right here is the base point x sub I. This one will be x sub I plus 1. So in 2-point central difference, these 2 points right here will be connected to create a tangent line right there. So that will be our approximate derivative. Now for the true derivative, we have, okay, let's put some label. This one will be the approximate derivative, while this one will be the true derivative. Okay, so as what you can observe to the graph, okay, the approximate derivative is almost the same to the true derivative compared to the backward and the forward difference. As you can see, the difference is quite obvious. So you can expect when you use the 2-point forward difference and the 2-point backward difference, the error is much greater compared to the 2-point central difference. Okay, let's input the given right here. Okay, so in solving the equation for the 2-point central difference, we will be using two equations, one for this point and one for this one, and we will combine them by subtracting this point right here to this point. Okay, so let's put the equation for f of x sub I plus 1. This will be, okay, by the way, the equations that we are looking for these points is actually derived earlier, this one and this one. So we're just gonna subtract this to this one to arrive at the formula for the 2-point central difference. Okay, let's put the formula. And in 2-point central difference, okay, let's put it right here. We will be considering 3 terms of the Taylor series. Okay. Okay, that's it for the point x sub I plus 1. And this symbol that we have in our equation represents any value from x sub I to x sub I plus 1. Okay, how about the equation for the point f x sub I minus 1? And this symbol that we use for the second equation represents any value from x sub I to x sub I minus 1. Okay, now we will be subtracting this one right here, f of x sub I plus 1 minus f of x sub I minus 1. We will get this equation. Okay, so now we already derived the formula for our 2-point central difference. Okay, this one right here. So the second term also represents truncation error of OH squared. So notice that this error is in second order compared to forward and backward difference, which is in the first order. So as we said earlier, the accuracy of the approximation depends on the order of the derivative that we are using. So notice that the truncation error of the central difference is of the order of h squared, while the forward and the backward difference is of the order of h. This indicates that the central difference approximation gives a more accurate approximation of the derivative. So later on, we will be solving problems to prove this idea that the higher the order of the derivative that we are using, the higher the accuracy is. Okay, so but before that, let's move on to the fourth one. Now, if you wish to derive a formula for a forward difference with the truncation error of OH squared, you can follow the 3-point forward difference. So basically, this is the same with the 2-point forward difference. The only thing that differs is that you would just add another point to the right of the base point. So consider this graph right here. Okay. And the base point right here, x sub I. And the first neighboring point right here is the x sub I plus 1. And the second one is the x sub I plus 2. So we're just gonna consider the first 2 points to the right of the point x sub I, which are the x sub I plus 1 and the x sub I plus 2. So the same process, we would just gonna draw a tangent line that connects the base point and the two neighboring points. So that one will be our approximate derivatives, while right here is the true derivative. Okay, so we will just use the formula for the 2 points. So for writing the value of the function at point x sub I plus 1 and x sub I plus 2, the following equation can be used. Okay, this one, x sub I plus 1. Okay, again, for the equation f of x sub I plus 1, we already derived it earlier, so we can use that one right here. Okay, this symbol right here is the same variable that we used earlier from x sub I to x sub I plus 1. And now for f xi plus 2, so again, the symbol is the same with the one that we have earlier. It's just the distance from the point base point x sub I to x sub I plus 2. The two equations are then combined such that the terms with the second derivative will vanish. This will yield as the equation. Okay, this is it. This is our formula for our 3-point forward difference with the truncation of OH squared. Right here. So let's compare it to the forward difference for the 2 points. Forward difference. Okay, as you can see, the error that we have is just in the first order. And right here for the 3-point, we have a higher order which is in the second order. Okay, so this solution is the same for the 3-point backward difference. So the formula for the 3-point backward difference is just this one. So let's try to solve a problem using some of the equations we've derived. Okay, for our problem 1, consider the function f of x is equal to x cubed. Calculate the first derivative at x equals 3 numerically with the 2-point forward difference and the 3-point forward difference. Okay, so in this problem, we are asked to solve the first derivative at x equals 3 using two formulas. One is the 2-point forward difference, and the second is the 3-point forward difference. Okay, so before proceeding to the solution process, let us first identify what are the given. For the base point x sub I, we have 3. So we will be using the x sub I plus 1 as the nearest point, which is 4. And x sub I plus 2 is equal to 5. Now, h is the distance between these points. Now, we have the value of 1. Now, substituting x sub I into the function, we will get 27 sub I plus 1. We have 64, and fx sub I plus 2, we have 125. Now, before using the formula for the 2-point forward difference and the 3-point forward difference, we will solve first for the value of the true derivative so that later on we will be able to compare our approximations to the true derivative. So for the true derivative, let's put it right here. 3x squared. Let's substitute the value for x sub I. We have 3 times 3 squared is equal to 27. Okay, now let's start solving the first derivative using the 2-point forward difference. Okay, for the formula for the 2-point forward difference, let's just use the one that we derived earlier. So it is this one. So the second term represents the truncation error, And later on, we will be solving how many percent error did we commit during the solution process. Okay, now, since we already gathered the given, let us just input the needed values for our variables here in the formula. So for this one right here is 3. We have 64 minus 27 over I. We have 37. Okay, so now calculating the truncation error, we have the absolute value of our approximation minus the true derivative over the true value for the derivative. So we get the value of 0.37 or 37%. Okay, so now let's use the 3-point forward difference and compare how many percent is their difference in terms of the error. Okay, let's start with so for the formula for the 3-point forward difference, we have okay, let's substitute the values needed here in our equation. We have negative 3 times 27 plus 4 times 64 minus 125 over 2 times 1. Okay, so using your calculator, we will arrive at 25. Okay, so calculating for the truncation error, okay, the absolute value of our approximated value, which is 25 minus the true derivative over true derivative. So we will get 0.074 or 7.4%. So as you can see, when using 3-point forward difference, you just committed a very small error compared to the approximate that you will get when using 2-point forward difference. Okay, it differs by a lot of percentage. So it is really advisable if you want to have higher accuracy when doing approximations to use this formula. For problems requiring higher order of derivative, we can use the formulas listed on this table. Okay, so here is a list of different formulas of various accuracy that can be used for numerical evaluation of first, second, third, and fourth derivative. Okay, so what we've discussed earlier is the difference formulas on the first derivative. So when you want to solve using the second derivative, here are some formulas that you might use. Okay, so the derivation process is just the same with the first order. The only thing that differs are the points, are the number of points that being used. Okay, just like this one, there is a formula for 3-point, 4-point, and 5-point. Okay, and the truncan error depends to the points, to the number of points that being used. The good thing here in finite difference formula using Taylor series is that you can just apply any of this equation depending to what the problem is asking for. For example, if the problem you are solving requires a 2-point backward difference, you're just gonna use this equation. Okay, so what we did earlier is that we derived the formula of based on the Taylor series expansion. So that's it for our video today. I hope you learned something and see you next time. Bye.